You got it? Okay. Oh, excuse me. It's the board cleaner. Still in the air. Goodness gracious. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray that you be glorified in what we do today, that we would just understand a little bit more about how to integrate things and this technique of partial fractions, Lord. In your name I pray. Amen. So before I get to the partial fractions, I just want to give you just a few sort of big picture examples for the, I don't want to carry out the whole integration. I just want to start us on a couple of trig substitutions. So let's see here. Oh, if I was smart, I'd do it over here, huh? Let's see here. Number 31. Ooh. Okay, and then before I get carried away, is there anything you guys have a question about? So I'm trying to take a little time to do what we were doing last time, just a little bit more. But this would also be the appropriate time if you have a particular question about a homework from this section. Yep. Number 60 from 8.2. Ah. Other questions? So I'm getting it all out here. All right, I think I'm just going to stop there for now. And then after this, we'll do the partial fractions, okay? I'll start with the gentleman's homework question. And so the question is to find the volume of revolution for y equals x sine x. And we're rotating around the y-axis, right? Now, if you try to use the method of washers to do this, right? So that's, it's kind of like one of those, like if you ever seen those Jello molds, like a ring of Jello. Ever seen one of these kind of things? It's kind of like that, but with no center. If you were to try to cut this up into discs, to washers, the difficulty is the inner radius and the outer radius both depend on the function y equals x sine x. So how do you separate the left and the right? It's a very cumbersome problem. So what you want to do instead is use the so-called method of cylindrical shells for this problem. So the method of cylindrical shells says what you do is you parse the thing, you cut it up, chop it up into pieces, and the pieces are going to be here's a picture of the cylindrical shell as it intersects the xy plane. All right, so the thickness of the shell would be dx, and the radius of the shell would be x. The height of the shell would be y. So if I was to draw the shell down here, it would look more like this. Right? Now think about this. So that if I take that and I lay it out flat, right, you'd have a rectangular slab, and it would be easy to figure out the volume of this infinitesimal slab. See, because the thickness of the slab is dx, right? The radius, right, the radius here is r. Well, the radius is also x. The radius is x, right? So this distance, because it's the perimeter of the circle, right, that would be 2 pi x. So I'm just thinking about cutting this and just laying it flat. And you see you can form this whole shape by gluing such cylindrical shells together, right? I would say like an onion, but that's not really how onions work. They're kind of more like spherical shells, right? Anyway, so over here we've got y, but y is equal to x sine x, right? So what's the volume for this infinitesimal thing? It's the area, which is 2 pi xy, times the thickness, which is dx, right? Area times thickness gives me volume. And this is true from 0 all the way out to x. I only need, if I get x, I automatically get the minus x on the other side because the shell sweeps all the way around. And then, of course, this is actually 2 pi x squared sine x dxy. Because x times the x there gives you x squared. I mean, sorry, the x here gets multiplied by x sine x, gives us x squared sine x. So long story short, to calculate the volume, all we've got to do is integrate. We have to calculate the total volume. What do we do? The volume is going to be equal to the integral from 0 to pi of what? Well, 2 pi x squared sine of x dx, right? And that integral you can do with integration by parts twice. Or the reduction formula if you like. So show of hands, who did not see the cylindrical shell method in Calc 1? Okay, so that, for those of you who are uncomfortable with what I'm doing, it might be good to take a look back, and I think it's in chapter 6. I haven't had the pleasure of teaching Calc 1 out of this book yet, so I'm not sure right off the top of my head. But yeah, I think it's section 6.3 if you need a refresher on some of these things. Yep. If you look at section 6.3 volume by the shell method, that will give you something beyond just our discussion here. But really, if you understand the idea of slicing it into disks or other cross-sectional methods, this is a natural extension, right? Hopefully you saw enough in Calculus 1 that what I'm doing here is not too mysterious, right? All right. Next, I'm going to jump over here. So now, my basic. I just want to tell you how would we set up this integral? What would your starting point be? I guess my starting point here would be. I didn't already talk about this with you guys, did I? I think I talked about this with the later section, but not with you guys yet. So my observation is that this is really du divided by the square root of 9 minus u squared. For u equal to what? Right, e to the x, because then e to the 2x is e to the x squared, which is u squared, right? And du is e to the x dx, right? So that's a starting point. And then how would I do this integral? I mean, I guess you can go back to the. So there's an overlap in ideas. If you're really fresh on the chapter 7 stuff, some of these integrals you just take as basic, right? You'd be like, well, wait a minute, that's just inverse sine integral if I factor out 9, right? But there's another way you could think about it, which is just to make a trig substitution. So some of the integrals in chapter 7 you could now do with trig substitution if you don't recognize it off the bat as being a basic integral. So I'm going to take that viewpoint here, and we'll set u equal to. If we set u equals to 3 sine theta, I think we're good to go. See, because then 9 minus u squared would be what? Right, which would be cosine squared theta, right? And so forth. So that's where I would start with the trig substitution there. Tell you what, I'll even do this one just to do something. So what's the du? 3 cosine theta d theta, right? So divided by what? 3 cosine theta? Because the square root of 9 cosine squared theta is 3 cosine theta. Well, this one's kind of funny, isn't it? The integral of d theta. So, theta plus the constant. But then that's what? This is inverse sine of what? U over 3 plus a constant, right? Because if u is equal to 3 sine theta, that says sine theta is u over 3, which means that theta is inverse sine of u over 3, right? But what's u? E to the x, right? So we get inverse sine of 1/3 e to the x plus a constant. Now, it's been a while since I looked at which problems I actually picked for you out of this section. If I've inadvertently done one of your homework problems, my apologies. I know you'd be very upset if I had happened to do that. But anyway, that's how that goes. When this happens, what that probably means is that we could also view this as like an elementary integral if we have a complete working knowledge of Chapter 7 material. Any questions about that? All right, I'm not going to finish these two. I'm just going to get these started. But how would we start this? We had to come to terms with what in the world this is, right? So I did some really simple completing the square last time. This one's a little bit more complicated, but that's really the heart of the matter. How does the square complete? So I've got minus x squared plus 6x, right, minus 8. So my first move, because I do not like to work with minus x squared, is to factor out a minus 1. And then I'm going to have to work inside the parentheses. So I've got x squared minus 6x plus 8. You guys with me? If I have a 2 there, my tendency would be to factor the 2 out. I want to work with a monic quadratic. I want to work with a quadratic where the coefficient of x squared is 1. Various other tricks exist, but this is just what's convenient to me. So minus 1. And then I do x minus 3 quantity squared. What does that do? That adds 9, doesn't it? But you know what? I've only got a what? I've only got 8, right? So this is minus 1. But then I can distribute the minus back through, and what do I get? This is really 1 minus parentheses x minus 3 quantity squared. Now, what I did in the purple is my way of seeing it. If you have a different way of seeing the end result, which I'm about to underline in green, you're welcome to do that. I want you to be able to think, right, for yourself as well. You don't have to follow my algorithm. But then once we have that, you see, what's this suggest the trig substitution should be? I'm just going to focus on trig substitution. I said what I wanted to say about hyperbolic substitution yesterday. Unless you guys ask me another question about it, I'm not going to say much more about it for now. So what is that? Not sine, right? Sine works for what? Something, wait a minute. Oh man, again? Fine. Boring. I was trying to pick out different ones. The same stupid substitution. This one. There's no 3, but it's the same something minus something squared, right? Constant minus the variable squared is a sign substitution. So to carry that out, you'd have what? You'd have integral of 3 plus sine theta times, what's this work out to? Cosine theta. And the dx is cosine theta, d theta. But anyway, I was trying not to get into all these details. The point is you make an x minus 3 equals sine theta substitution there. Any questions? Or?
Can you explain that last part with the 2 cosine?
Yeah. So, run out of room. So if x minus 3 is sine theta, right? 1 minus x minus 3 quantity squared is actually 1 minus sine squared theta, right? Which is, by the way, cosine squared theta. So the square root of 1 minus x minus 3 quantity squared is cosine theta. That is the first cosine theta from the root. The second one is that this is dx is equal to cosine theta d theta, right, if I differentiate. So this one is this one. And then, of course, x you can solve. X is equal to 3 plus sine theta. Oh, at which point you've got an integral of like sine and cosine. You can do those by u substitution in this case, I think, even. Okay, so then this one, what do I want to do? Again, complete the square. Let's see here. So this is x squared minus 2x plus 3 is equal to x minus 1 quantity squared plus what? Plus 2, right? Finally, a different pattern, I think. All right, so this is a what? We use a what? Tangent substitution on this one, right? So this, to me, suggests that I should make a x minus 1 is equal to the square root of 2 times tangent theta substitution. Because, I know, if I do that, x minus 1 quantity squared plus 2 will be equal to what? It'll be equal to 2 tangent squared theta plus 2, which is what? That, yeah, indeed, that is tangent squared plus 1 is secant squared theta. Again, it goes back to the table I wrote here yesterday, which you need to work enough problems that you understand what's going on here. I'm just trying to give you another example. And so x would be what? X is 1 plus root 2 tangent theta. This is the square root, so that actually ends up being the square root of 2 secant squared theta, right? And then what's the dx? Dx is square root of 2 secant squared theta d theta. And then you have to work that out. I don't really think this is a technique you can learn from just watching me. You really have to try to do it yourself in homework as well. Okay, that's generically true for almost everything in here. I can try to show you how to do it, but I know you don't really understand it until you just sit down and try to do it for yourself. That's just the nature of this course. But are there any questions? So what I'm trying to tell you is if you don't understand what I'm doing, but you haven't actually tried to sit down and do the homework yet, I wouldn't feel too bad, right? But you'll get more out of my lectures if you try to do some of these homeworks before I'm actually doing them, right? If you think about it, if you take say 10 minutes the day before to try to do one of these. When you see me trying to do it the next day, it'll make a lot more sense. I mean, you'll get more from the lecture. But I don't know, some of you are like, but I have other things to do with my day besides calculus too. Fine, I understand. I get it. Or you might be like me, you're just waiting to see what the professor does before you try to do it yourself. That's understandable. Okay, so that brings us to the next technique, which is the technique of partial fractions. So here's the problem. I believe, oh, I'm sorry. So one of you asked me what section this was in the textbook, and I think it's 8.5. Yes, section 8.5, rational functions, partial fractions. So partial fractions is the technique, rational functions is the target. Our goal is as follows. Integrate f of x equals to p of x over q of x, where p of x and q of x are polynomials. In other words, we would like to know how to integrate rational functions. Now, I would encourage you to notice that we already know how to integrate a wide variety of rational functions. Let me refresh your memory. What we know. How about this? If I have the integral of dx over x minus a, what's the integral? Or integral of dx over x minus a squared, etc. Integral over dx over x minus a. Well, I guess that suffices. Well, fine, x minus a to the n. This one is natural log of the absolute value of x minus a, right? This one is minus 1 over x minus a. This one is, let's see here, 1 over, well, minus 1 over n plus 1 times x minus a to the, oh, I'm sorry, I'm an idiot, n minus 1, right? No, n plus, wait. 1 second here. Think for a second here. We have to raise the power of the power function, which means we lower the power in the denominator. Yeah, of course. But in view of that, this is supposed to be what? N minus 1. So basically, if we have a linear factor to any power, a reciprocal of that, we can integrate it, right? Agree? This is Calc 1 stuff, really. What if we have the integral of dx over something like, say, x minus alpha squared plus beta squared? For this, we could make a x minus alpha is equal to beta tangent theta substitution. Right, if I make this substitution, what's x minus alpha squared plus beta squared? It's exactly equal to beta squared secant squared theta when you work that out. And so you see what we have then is we've got beta secant squared theta d theta divided by beta squared secant squared theta. Much like the one I just erased, the trigonometric functions cancel out. I mean, this is really just kind of a twisted chapter 7 integral, right? I mean, it's essentially just 1 over beta. I mean, it is exactly this. I don't need to use the word essentially. It is this. And you can integrate, right? That's 1 over beta theta plus a constant, which is what? 1 over beta inverse tangent of what? So if we have an irreducible quadratic, a quadratic which can't be factored over the reals in the denominator, we can integrate like this, right? What if I have 1 over an irreducible quadratic squared? So like the same thing but squared, how would I do that? I mean, forget the square. Let's just do the nth power for n greater than or equal to 2. By the same trig substitution, this is the integral of beta secant squared theta d theta. And what do you got? You've got beta squared, you got beta, you got beta times the secant of theta to the what power? So what's inside the brackets is actually beta squared secant squared, right? So this would be beta secant squared to the n power. It's in other words beta times secant to the 2n power. Or just to kind of put a stake in it, this is 1 over beta to the 2n minus 1, the integral of cosine to the 2 times n minus 1 theta d theta. Now, my point to you with this formula is not that we're going to try to work this out for all n. You should recognize at this point those are integrals that you can do. It's cosine to a power. That integral's in our house now. We can shoot it if we want, right? This is Virginia, right? Are you allowed to shoot people in your house in Virginia? I mean, if they don't belong there, not just for fun. Sometimes just for fun. I mean, if you watch the local news. Alcohol is usually involved. But, or prescription pharmaceuticals of some sort. My point to you is that we can integrate any kind of rational function like this by this kind of trig substitution, right? I think at some point I even have done this for maybe just a square, right? I'm not going to go further on that. All right. So you're like, okay, well that's fascinating, but the other thing. One other thing. What if we have the integral? What if we have a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus da 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 da, plus a1x plus a naught. Can you integrate this? You should be like, yeah. Like, okay. Obviously. Please put more of those on the test, right? Without the annoying arbitrary constants. But my point to you, of course, is we can integrate any polynomial, right? So here's the giant claim. Here's an algebra fact. All right. And this fact I'm referring to is the partial fractions decomposition. In words, any rational function permits a partial fractal decomposition. In words, that is, we can write f of x equals to p of x over q of x equals to a polynomial plus a sum of basic proper rational functions. What do I mean by basic proper rational functions? Basic proper rational functions include in their number things like 1 over x minus a, 1 over x minus a quantity squared, 1 over x minus a quantity cubed, and so forth, to any finite power, and 1 over x minus alpha quantity squared, plus beta squared, 1 over x minus alpha quantity squared, plus beta squared, squared, and so forth. The way this is actually carried out is it's a basically 2 or 3 step process. How about try to here's basically the process. Step 1, you're given a rational function, all right? So let's say f of x is equal to p of x over q of x. So step, what you do is perform long division if needed. To write f of x is equal to, let's say, m of x plus r of x over q of x. When you do this, what's left here, this r of x over q of x, will be what's called a proper rational function. A proper rational function I call those basic proper rational functions. What's common to all of those is that the degree of the denominator is strictly larger than the degree of the numerator. Right? So an improper rational function would be something like here, maybe it'd be helpful for me to start doing an example as I give you this algorithm here. I'll tell you, let me just finish the algorithm, then I'll do the example. Don't get things too cluttered. Step 2 is you completely factor q of x over the reals numbers. So what that means is q of x is going to look like what? It's going to look like something like x minus a1 x minus a1, and then you have x minus a2 x minus a2 and then you've got stuff like x minus alpha 1 squared plus beta 1 squared. I guess I could kind of be more greedy and just say that this is to some power, say r1. And then you'd have like x minus alpha 2 squared plus beta 2 squared to the r2 power, something like that. What I'm trying to get across here is you completely factor the polynomial in the denominator into a product of linear factors, possibly repeated, and irreducible quadratic factors, possibly repeated. We can do this because there's this thing called the fundamental theorem of algebra, which says that any real polynomial factors completely over the complexes, right? But over the reals, sometimes we get these conjugate pairs, right? The conjugate pairs collapse to give us the irreducible quadratics. But that's all there is. It's either irreducible quadratic or it's a repeated linear factor. That's it. End of the story. That's it. And then step 3 is you construct the partial fraction. This is where the fun is. Decomposition for let's say r of x over q of x is equal to something like a over x minus a 1. So I'm just for the sake of this, let's suppose that there are s of these, s1 of these, okay? So I would have like a over x minus 1 plus b over x minus a1 squared plus da da da. Ooh, I regret my alphabetization will not do us well. Let's call this a1. Let's call this a2, big A2, all the way to big A s1 over x minus a1 to the s1. Well, let me just say plus dot 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 dot. Let me show you with examples. There's no point in me trying to write this out in general. Let me see if the book actually has an attempt at the general partial fractions decomposition. So the way the book handles this is he gives you a couple thought boxes, like page 424. He basically has this idea that deals with just the factors based on root a1. And then he's got another blue box on page 425 to deal with the irreducible quadratic factor. And then on page 426, he tells you what the story is for each irreducible quadratic factor. That's probably a good approach. So my point is, these guys, all right, these are all just coming from the x minus a1 to the s1 power, right? So these ones right here, you get these by doing something like, let's say, b1 over x minus alpha 2 squared plus beta 2 squared. Well, I would say this, b1 plus b2 times x minus alpha 2. Oh, fine, b1 plus c1. And then plus da 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 plus b r2 in my numbering plus c r2 x minus alpha 2 over x minus alpha 2 quantity squared. Oh, I'm sorry, I regret trying to express this at the start of it. I should have showed you an example first. If only I had another chance to lecture this material today. Do a better job. You guys really get a bad deal. You guys are you're just the warm-up for the real lecture. Sorry, I shouldn't talk to you this way. It's not nice. Okay, so let me try to show you how this goes. So for example, if I have 1 over x squared times, say, x minus 1 quantity squared plus 3, just like that, then what I would do, the partial fractions decomposition is this. I do a over x plus b over x squared plus, and here's the thing, c plus d times x minus 1 over x minus 1 squared plus 3. That would be the partial fractions decomposition. Now, it's not done. You actually have to do algebra to figure out what a, b, c, and d are. Why would we do this, though? What's the whole motivation? Again, our goal is to integrate rational functions, right? Check it out. If that's true, if that's true, the left-hand side, I can't integrate, right? But the right-hand side, it's this stuff. So we can integrate, right? You can integrate these things. Oh, I guess I'm missing something from my list. How would you integrate something like the integral of x minus alpha dx over x minus alpha squared plus beta squared? I'm just going to write down the answer. It's 1/2 the natural log of x minus alpha squared. And what did I do? Oh, no, sorry. Uno momento. I should say minus 1 over x minus alpha quantity squared plus beta squared, I think. No, that's still wrong. Man. Fine. I guess I shouldn't just try to do it in my head. This is a u substitution, right? I can do this as integral of 1/2 du over u. I'm saying the denominator is u, right? See that? Because the derivative of this is 2 times x minus alpha. So that gives me 1/2. And anyway, long story short, that's 1/2 natural log of x minus alpha quantity squared plus beta squared. I don't really need absolute value there because that's a positive thing. You could pull the 1/2 inside if you like. This is the natural log of the square root of x minus alpha squared plus beta squared plus a constant. A lot of people like to write it that way. Okay, so there's the other thing that can happen. That's the other thing I need for the... And there's some kind of corresponding thing that can be done for this as well. All right. I want to actually show you one. I hope I have time. Oh, man. Oh, we're okay. We're okay. Let me get a little bit more mileage out of this example, then I'll show you an explicit one. Next class, we're just going to do, this is the general picture. This particular method, I feel like you have to give the general picture at the start. Otherwise, people are just going to be asking questions about, well, what are you going to do with that? And what about that? And what about that? And what about... I'm trying to tell you about what about that at the start. If I instead put a cube here, then I have to add more terms. Then I get plus e plus f times x minus 1 over x minus 1 squared plus 3 quantity squared plus g plus h times x minus 1 over x minus 1 squared plus 3 quantity cubed. Yeah, thanks. Here's a general rule of thumb. There should be as many undetermined coefficients in your partial fractions decomposition as there is a power in the q of x. So like here, q of x has, this is square, this is 6. 2 plus 6 is 8. There's an 8th order polynomial in this denominator. How many constants do I need? 1, 2, 3, 4, 5, 6, 7, 8. Not an accident. All right. Let me try to show you an example. Suppose we wish to integrate dx over, let's say, x times x squared minus 1. So, first of all, I don't even have to bother with this first step because it's already a proper rational function. I don't have to separate off a polynomial. That's good. So step 1 is done. So partial fractions says that I can take this x squared minus 1, and what do I have to do? I have to completely factor it, right? So this is x times x plus 1 times x minus 1, right? And if we believe partial fractions, it says that I can rewrite this as a over x plus b over x plus 1 plus c over x minus 1. So what we're doing is, you could call it reverse common denominatoring. Not actually a word, but that's what we're doing. It's like undoing a common denominator, right? That's the idea. Most of us can't just do that by looking at it, right? So we have to use some algebra to work it out. And that's what we do. So then the next move here is to multiply both sides by this denominator. So this gives me 1 is equal to a times x minus 1 times x plus 1 plus b times x minus 1 plus c times x plus 1. That's an important step. Let me give you a second to try to understand it. Maybe 10 seconds. Maybe even 20, I don't know. That marker's dead to me. Did you see what I did, guys? Why is there no, for example, why is there no x term on the a over x when I multiply? The x's cancel, right? The x plus 1's cancel with the b. The x minus 1's cancel with the c. So we got to solve this equation. Now the easiest way to do this kind of one, is just to put in different values for x and see what happens. If I put in x equals to 0, what do I get? 1 equals to what? That's gone. That's gone. X equals to 0 gives me minus a. Hey, check it out. A is equal to minus 1. There's 1 down, 2 to go. If I put in x equals to 1, what happens? Dead. 0. 1 times 1 plus 1, 2c. Right, so 1 is equal to 2c. So, c is equal to 1/2. What else? What do you think my third thing is going to be to do? Put x equal to what? X equals to minus 1. Very good. So then that kills the a term and the c term, and it leaves us with b times minus 1 times minus 2. In other words, 2b. 1 is equal to 2b. So therefore b is equal to 1/2. So in fact, through this bit of algebra, we have learned that 1 over x times x squared minus 1 is in fact minus 1 over x plus 1/2, 1 over x plus 1, plus 1/2, 1 over x minus 1. This is partial fractions. Don't be, if you don't understand this yet, it's okay. Once we've worked on this for a while, you'll come back and look at the process, and this thing I was saying down here will start to make sense. There's just some exceptional cases that you're going to have to see, and you won't really understand it until you see a few more examples. I'm sorry about this. I mean, it is what it is. So the integral dx over x times x squared minus 1 is actually equal to what then? Minus the natural log of the absolute value of x, plus 1/2 the natural log of the absolute value of x plus 1, plus 1/2 the natural log of the absolute value of x minus 1, plus a constant. And there you go. So are there any questions? I mean, there should be questions, right? You may not be ready to ask them yet, and that's fine. So Monday, we'll again do this, all right? Now, the homework on partial fractions isn't due yet, is it? That would be pretty mean if I asked you to turn in homework on partial fractions Monday, right? The homework which is due Monday is what? It's on trig substitution. It's on the last part of the integration by parts. It's on the integrals of trig functions. It's on that stuff mostly. So, have a good weekend, you guys.